inviting me to give a talk over here. And today I want to talk about my recent results on partial different sets in abelian groups. So first I will give some introductions. And so first I will talk about strongly regular graphs. So a finite graph is called a strongly regular with parameters v, k, lambda, mu, if it has v vertices and each vertex has degree k. And for any two adjacent vertices, they have lambda common neighbors, and any two non-adjacent vertices have mu common neighbors. And so next, I'm going to show you two examples. The first one is a very simple one. It's a pentagon. And so you can see that we have 5 vertices, and each vertex has degree 2. And for any two adjacent vertices, they have low common neighbors. And so that's why lambda equals 0. For any two non-adjacent vertices, they have one common neighbor. So that's why the mu equals to 1. So that's the pentagon. And over here, this is a graph with 9 vertices. So each vertex has degree 4. For any two adjacent vertices, and they have one common neighbor. And so those two vertices are adjacent, they have one common neighbor. For any two non-adjacent vertices, and those two vertices, they have two common neighbors, this one and over here. And so that's the two examples I share with you. So for strongly regular graphs, there are a lot of research going on if you search strongly regular graphs. A typical tool we use to study strongly regular graphs would be adjacency matrix. And so what we do is we try to label all the vertices, and then we will get a V by V matrix. And so if vertex I is adjacent to vertex J, and then at ij entry, we'll put 1, otherwise we put 0. So if you look at my the graph of pentagon, so vertex 1 is adjacent to vertex 2 and 5. And so at the entry 1, 2, and the entry 1, 5, we put 1, and the other positions we put 0 in the row 1. So that's the adjacency matrix, right? So that being studied well for the adjacency matrix of strongly regular graph, we know it has exactly 3 eigenvalues, and we also load the multiplicities. So here I want to emphasize one thing. Most of the cases, the eigenvalues are integers of the strongly regular graph, except special case when gamma is a converse graph on V vertices when V is not a perfect square. So the converse graph is a strongly regular graph with the special parameters over here. So if the parameters are V minus 1 over 2, V minus 5 over 4, V minus 1 over 4. So that's called a converse graph. And so only when it's converse graph, when the V is not perfect square, otherwise the eigenvalues are all integers. We care about this condition because later that's part of the requirement for my theorem. So now, finally, we come to the main topic, right? So today I'm going to talk about partial different sets. And so here I want to talk about the definition. Suppose you have a group, a finite group G with order V, and D is a subset of the finite group with K elements. And then the D called Vk lambda mu partial different set if the set of differences GH inverse with G and H in D and G is not equal to H. If the set of differences represent each non-identity element in D exactly lambda times and non-identity elements of G not in D exactly mu times, and then we call the D to be a Vk lambda mu partial different set. Now, for us, we study the regular case. So what we require is the inverse of D equals to D. So the inverse of D is you take the inverses of all elements of D. So you got a new set. If the new set to be the same as the original set, and also it does not include the identity element, we call the D to be a regular. And so A regular partial difference set is called trivial if the union of D with the identity element, or the complement is a subgroup we call the trivial case. And we care about non-trivial case most of the time. Now, so partial difference sets were introduced by Bose and Cameron, named by Chakravarti. And Shunima has done a lot of wonderful study from 1980s. And so Shunima also wrote a well-known survey in 1994. And now partial difference sets, in fact, has it's a generalization of different sets. So if lambda equals to mu, then we know there are different sets, right? So now I'm going to draw the connection between partial difference set and the strong irregular graph. And so suppose D is a partial difference set, and you can construct a Cayley graph. And so what you do is you take the group elements as the vertices of the graph, and then you define their adjacency based on whether GH inverse belongs to D or not. So two vertices, G and H, we said they're adjacent if the GH inverse is in the set D, right? The connection is whenever you give me a partial difference set and then the Cayley graph, it is a strong irregular graph. And so that makes partial difference sets very interesting because it is very difficult to construct strong irregular graphs. And so if you have a partial difference set of the same parameter, we guarantee you can get a strong irregular graph, right? Of course, strong irregular graphs can be constructed in many ways. And so partial difference sets, it offers one of the way to construct strong irregular graphs, right? So now I'll give you a well-known example. This is called a Paley type partial difference set. And suppose you have Q is a prime power and Q congruent to 1 modulo 4. And then we know that must be a finite field of order Q. And what you do is you take the non-zero squares from the multiplicative group, and that's your partial difference set. And that partial difference set, it is in the additive group of the finite fields. So finite fields, you have two operations, right? And so you have multiplication and you have the additive group. And so you take the non-zero squares from the multiplicative group, but as different set will be in the additive group, right? Here we give you examples. So in the finite field of order 13, and so here are the set of non-zero squares, right? And then it is a Paley type partial difference set. And some of them it's easy to tell the square, right? 1, 4, and 9, that's easy to tell it is a square. And 3, it is congruent to 16. And so it's also a square. So you can check all of them, they are squares, okay? So the graph below, we built, so that's the Cayley graph of this partial difference set. And so it is a strong irregular graph with the same parameter, right? Okay, so that's the example. Now I'm going to talk about a relatively recent results we have done for strong irregular graphs. In fact, we call the Benson theorem. The reason is there's a Benson theorem for generalized quadrangles. And later, there's also similar results for partial geometries. And one of my collaborators, he's a finite geometer, right? And so because the point graph of those geometries are strong irregular graphs. And so it make us think about maybe similar results will hold for strong irregular graph, and turns out to be true. And people got very excited about this result. So, okay, so I'm going to roughly read about this result. So suppose gamma is a strong irregular graph. And now you can see why I really care about integer eigenvalues, right? That's part of the requirement. So most of cases, they are integers, so we don't worry too much. Now, suppose phi to be an automorphism of order n of gamma. So that's the automorphism of the graph. let mu to be the Möbius function, and then for all positive divisor d of n, and there are non-negative integers a sub d such that we have equation 1 to be true. So on the left side, if you recall my previous slides, so the k, mu2, mu3, the eigenvalues of the adjacency matrix of the Stroninger graph, right? And on the right-hand side, mu3, that's still the eigenvalue. So F, it is the number of fixed vertices of phi, and G is the number of vertices that are adjacent to their image under phi. And so it's very nice result just on its own, right? So you connect the property of the monomorphism of the graph with the eigenvalues of the graph, right? So that's equation 1. And now, since there's close connection between Stroninger graphs and partial different sets, and so it's natural to say, can we apply this one to partial different sets to get some application? And turns out Shunima has a wonderful table waiting for us. And so first I want to talk about a coronary, and then we're going to apply to partial different sets. All right, so the coronary says, suppose G is a Stroninger graph with integer eigenvalue, and let phi to be an automorphism of order n of the graph. Let S to be co-prime with n. And then it follows that phi and phi to the S maps the same number of vertices to adjacent vertices. This easily from previous theorem. Okay, I can show you. So remember, phi and phi to the S are both automorphism of the same graph. So on the left side, everything the same values on the left side in equation 1. And phi and phi to the S, they have the same number of fixed vertices, so the F value is the same too. And so of course, then it follows the G value is the same for phi and phi to the S. So that easily follow from equation 1. So the only requirement require S to be co-prime with N, because we want them have the same number of fixed vertices, right? Now, based on that, we came up with the results on partial different sets. So let D be a regular partial different set in an abelian group G. So previously, we don't require anything. Okay. All right, anyhow, so now we talk about partial different sets. So we require the group to be abelian, all right? That's important for us in this result. We require to be regular PDS. That's because then the Cayley graph coming from D will be non-directed, all right? And no loops also, okay? That's why we require to be regular PDS in abelian group G. Now assume delta to be a perfect square. So if you recall some of the eigenvalues, and so this will guarantee that the eigenvalues will be integer. That's why we require delta to be a perfect square. So now let U to be an element of R. We assume S is co-prime with R with the order of the element. And then what we claim is U belongs to D if and only if U to the S belongs to D. So probably see, okay, that condition looks the same as the coronary co-prime with order, and easily follow from the coronary. That's because whenever you have an element from D, you can easily define a corresponding automorphism. And so you just map any element. So, okay, so here I should just call vertices because you can always get a Cayley graph based on the partial different set, right? And so you map the vertices V to VU, and so you have the automorphism U, right? And so you can easily argue that the element belongs to D if and only if the corresponding automorphism maps all vertices to adjacent vertices, right? The only thing is we need to require the group to be abelian, and then you can have this result, right? And so, and then follow from the corollary, and this theorem will follows, okay? Now, this result give us very good grip on the elements. Here it says, if you know one element in a set, and now you know a whole set of it, all right? So suppose my group element, so of order 7, it is in D, and then what we can say is, will be u squared, all the way up to u to the 6 will also be in the set, all right? So it tells us a lot of information corresponding to this element, all right? That's why we call the local multiplier theorem, right? So our local multiplier theorem easily imply the classical multiplier theorem. And so the classical one talk about, suppose you have a regular partial difference set of order V, and assume there had to be a perfect square, the same requirement, and then D to the S equals to D for all S co-prime with the order of the group. And so that easily you can prove use our local multiplier theorem. As I mentioned before, Shunima has very nice table waiting for us to solve. And so in 1994, Shunima wrote a survey paper. In this survey paper, and there are 32 cases were open. And so what he looked at is for the size of the partial difference set to be smaller or equal to 100, right? And most of cases he can get rid of. So either say they exist or does not exist. But there were 32 cases were open. And in 1997, he offered more conditions. And so he get rid of a lot of 13 cases. And then in 1998, Frank Fitner and Michel Klein discovered a new PDS, which is in the list, which were open, right? So now we have 18 cases left, right? And so now I'm going to show you the table, which was left open. And so we started research in 2014. And so we were not sure, say, okay, after 1998, still open, we were not sure. So we wrote to Shunima, and Shunima replied us very quickly. He said, yes, as far as he knows, it is open. So that's very good news. And now I'm going to show you a direct application of our local multiplier theorem, right? Before that, and I want to talk about restriction of the group. And so this gives a structure of what kind of group you can have non-trivial PDS. So this one says, so if you have a abelian group G, if you have a cyclic CeLO-P group and your group G, the order is not P, and then you cannot have non-trivial PDS, all right? And another case is also forbidden is, so if you have a abelian group and you have a CeLO-P subgroup isomorphic to Zp to the S by Zp to the T, S is not equal to T. If you have CeLO-P subgroup like that, then you cannot have a non-trivial PDS. So in fact, this result related to Schering result. So we try to make some improvement of this preparation. It is pretty difficult for this structure. So, okay, this is very useful for us. So now the next one is one of the parameter is 196, 65, 24, 20. So 196 equals to 4 times 49. And so by the previous preparation, we can say that the structure of the group has to be Z2 by Z2 by Z7 by Z7. So you cannot have a CeLO two group cyclic Celo 2 group, you kind of have cyclic Celo 7 subgroup, all right? And so it has to be like this structure. So then we know that the only possible non-identity elements, the orders will be 2, 7, or 14, okay? And we care about the Euler phi function of those orders. So Euler phi function of 2 is 1, of 7 is 6, of 14 is also 6. So we care about how many numbers are co-prime with those numbers, okay, up to the number, right? That's because of my local multiplier theorem, we care about that. And so maybe we go back to the local multiplier theorem one more time over here, right? So if you have one element, U, and then U to the S will also be in D whenever your S is co-prime with the order, right? That's why I care about the Euler phi function, right? So if you have an element of order 7, and then right away, I know 6 of them will be in D, right? All the power, okay, up to U to the 6, right? So that's why we care about this. So then we can write down, so this 65, that's the size of the partial difference sets. And so R1, that count how many elements of order 2 will be in, we don't know, R1. And R2, that's the number of elements of order 7 or order 14, because the Euler phi function, both of them are 6. That's why R2 times 6, right? And so that's the size of the partial difference set. So because you know one of them, you know a whole set of them, right? So from here, you can see that 65 will be congruent to R1. And R1, that's the number of element of order 2. So at most 3, right? Because from the structure, you can see at most 3 elements of order 2. But on the other hand, 65 is congruent to 5 modular 6. And so this is impossible. So right away, we prove this case does not exist.
Here's one question.
Yeah.
Yeah. Can you see something about strongly regular graph with these 196 parameters?
No. So I only can talk about the PDS. So we have cases. Okay. So I can see here. So for example, I think it's this parameter. Either this one or the one below, we can prove that there's no regular PDS in a abelian group.
Yeah.
But they do have strongly regular graphs.
I see.
Yeah.
Yeah. Thanks.
Yeah. I think that was a very recent paper. They did construct strongly regular graph with parameter, but we don't have partial difference sets in the abelian group.
Yeah. Yeah.
Hey, could I also ask a question before you go on?
Okay.
I've not understood something. Could you explain why this result cannot be obtained from the classical multiplier theorem? If D is equal to the image of D little bracket S, then doesn't that mean that D is composed of as a union of orbits? So why is this giving something new?
So I would say it's easier to I would not say that from the classical one, you cannot imply it. So one thing I didn't say is, so after we got our local multiplier theorem, right? And we did try and we succeeded to prove our local multiplier theorem from the classical one afterwards. So I would say, I don't say one is stronger than the other one, but I think the local one, sometimes when you attack a question, maybe have more grip in the beginning.
I see. Okay, thank you.
Yeah. So we did, I think in our paper, we did give the proof from the classical one to the local one, but that's afterwards. We didn't see that in the beginning, but afterwards we say, okay, we can prove it, but we used a strong machinery to prove it. All right. All right. So I don't want to talk about other techniques we used, but I just show you for this table, after that paper, we have 2 cases left. And in this table, there are 6 cases kind of interesting. So 100, it is 4 times 25. 196 is 4 times 49. And so this is 4 times 5 squared. This is 4 times 7 squared. And so my co-author, Dee Winter, so he gave a talk at the URC conference. And so Jim Davis was one of the audience. So he said, okay, can you generalize to the case when the group order is 4p squared, when p is prime number? And so that's how we start to look at our next question. So let's talk about general case. And so what do we know about this situation? We know this group structure. So that's follow from the preparation. And we know a sporadic case. And we know the other cases, a non-trivial cases, just the PCP type. And the difficulty is the possible parameters increase dramatically with P. When P is big, you imagine, right? We talk about, okay, P is prime number, yes, but when your prime number goes big, and then there are too many cases. So that's a challenge. And so first I want to talk about PCP. So PCP partial difference set is, so first you have a group of order and square. And if you have a set of subgroups of order n, and those subgroups, suppose they only share the identity element, right? And then what you can do is you take the union of those subgroups and get rid of the identity, and then it is a regular partial difference set. So that's a type we call the PCP type of partial difference set. And so here we give an example. So those subgroups, they only share the identity element. And so, right. Now, we came up with a completely new strategy. So far, we only used in this case. So what we do is we use the elements of order 2 and identity element as the index for the row. So G1 is the identity element, and G2, G3, G4. So you have 4 rows. And then the columns, we use the subgroups of order P, right? So you have P plus 1 of them. So you have 4 rows and P plus 1 columns, right? And then we define the cosets. So you have the element GI and times HJ, and then but you get rid of the GI, right? And so that's our Sij. So we basically partition the whole group elements into blobs, okay, Sij. The only thing we didn't put in are the identity elements and the elements are order 2. And with those we put here aside, right? Everything else we put in blobs. And because our local multiplier theorem, we can say is, so the Sij, either you have everything in the D or nothing in the D. So here it says one element is in, the whole thing is in, right? So we think that's a very good partition, okay? And so if Sij in D, then we put the corresponding entry to be 1, otherwise we say it is 0, okay? And so you don't need to worry about the identity element and element order 2, because that's how we're going to do our discussion. So we call this as characteristic matrix. Now, you can partition the case either D contains no elements of order 2 or 1 element of order 2. Other cases can be the complement. And so here I give you one justification. And so if the first column of chi, it is 1, 1, 0, 0. And then we can describe the elements of Si1. So that's the first column can be written as a difference of elements of D in the different number of ways. And so that's the first one. So how many ways you can represent it by the difference of D? So that's a first entry. So those, so that's a first row, first column, right? Okay, and then that's a second row, first column, and then third row, first column, and then fourth row and first column. And so since I 1 and 1, and so those are elements should be in D. And so the first two, they should be lambda values. So this one and the one below, they're corresponding to lambda values. So that those two values should be the same. And then the last two, because they're corresponding to elements not in D, and so those two values are mu values. And so right away, you got two equations, right? So those two should be the same, first two, sorry, the last two should be the same. Probably wonder, so what are the R1, R2, R3, R4? Those are the number of ones in the, so that's the number of ones in the first row, the number of ones in the second row, and so on. And so here, R1 will be the row vector of the first row vector and the second row vector, and that's a dot product. So by doing that, and then you got quite some equations and you solve equations, right? And so you can figure out the values of R1, R2, R3, R4. Okay, so just give you a flavor of it. And by doing that, figure out if D does not contain any elements of order 2, you only have 5 possibilities of the characteristic matrices. And so that's corresponding to trivial case because that's a subgroup, right? And the last case is a PCP case. Because here you probably should put in the identity element, otherwise it's not going to be a group. And so. Now, if contains one element of order 2, and then we have 5 cases, and we are very excited for the last one because we did rediscover the special case, the sporadic one. And we can see how many columns should have. You can see other ones that generally have p+1 columns, but this one we can come down to all the details. It's just come out. So my collaborator and me, none of us, we like computer people that much. So we did everything by hand. So I believe you should be able to computerize it. And I think then things will be much simpler for computation. And so, yeah. So that's about, okay. So what we have proved is what we know, that's it, nothing else, okay? So trivial case, a PCP case, and the sporadic case, nothing more, so. Now, the next question is, we have 2 cases left. So those 2 turns out to be more different. And so finally, what we did is we tried to introduce weights for point and lines in projective plane. So we use a symmetric design to finally prove it. And so, yeah, so that's a nice 2 cases. And then, okay, since we, based on 6 cases, we look at 4p squared. So this one is special. So this is 2 to the 3rd times 3 to the 3rd. So we're thinking, how about 8p to the 3rd, right? And turns out this case is very different. So 4p squared, the open, so the possible parameters increase dramatically, but the 8p to the 3rd is very different. So we can describe the parameter sets completely. They only have 2 cases, okay, or 4 cases. So for each p, it's not, the number of possible parameters with each p does not increase. right? It's not like for p squared, when your p is big, the possibilities, it's huge. And this one is, even your p increases, each of them just have 2 or 4 cases, right? So that make it easier. I don't want to go into detail, but I just want to show you we did prove low non-trivial regular partial difference sets in abelian groups are order AP to the third when p is bigger or equal to 3. So the next thing I want to talk about is my recent, very recent results about the regular penny type PDS. And first, probably have seen these parameters a few times now, right? And so if you think about strongly regular graphs with those parameters, we call the conference graphs, right? Okay, so a partial difference set with those parameters, we call the penny type PDS. And there are 2 key problems. The first one is we ask for which odd part of the integer v can we find a regular penny type PDS in an abelian group of order v. Okay, so that's the first question. And second question is, given a group order, so in which specific abelian groups of that order can we find the regular penny type PDS? So the first one is asked about what kind of order you can find regular penny type PDS. The second one asks you about the group structure, right? What I focused on is question 1, all right? So first I want to talk about 2 results. So in 1984, Shunima proved, so if D is an abelian regular PDS, so suppose your delta is not a perfect square. And then he proved that, and then D must be a penny type. And also he loads the parameters. So the P will be a prime congruent to 1 modulo 4. So the V is a prime power. So if delta is not a perfect square, then he loads the structure, okay, structure. Now, another result is, as I shown before, if you have a prime power congruent to 1 modulo 4, and you can, because we have finite field of order Q, and then you can use the non-zero squares to construct a regular penny type PDS in FQ in an additive group, right? And so now, also the Paley type PDS, suppose you have a Paley type PDS, because of the parameters are so special, you can compute the delta, and the delta equals to V, right? And now, based on the math result and the classical construction, to answer our question, what we only need to focus on focus on when V is a perfect square and V is not the prime power, right? So the delta equals to V in this case. And so if V is not a perfect square, and Ma already told you, has to be a penny type, has to be a prime power, right? And then if you have prime power, you have, you already know the construction that surely guarantee that you do have a penny type PDS. In 2019, I have proved the following result. So let G be an abelian group of order V, and V here is the perfect square, and it's not prime power, right? So if there is a regular penny type PDS, and then for any I, if Ki is odd, and then we have Pi is congruent to 3 modulo 4. So we say if those Ki is odd, we can tell you some information about the Pi. Okay, so that's the first result I have proved. But turns out we can completely solve the question 1, and I didn't expect that at that time. So we need a math result from 1994. So Ma proved this result in the sub partial difference set paper. And in fact, I have been using this subset of partial difference sets results many times, but I didn't pay much attention to the second part. So okay, what does this result talk about is, suppose you have a partial difference set D, and you have a group G, right? And so now what you do is you take a subgroup from the original group, and now you do intersection with your partial difference sets, right? And now the intersection, the math result says the intersection, which is D1, remains to be a partial difference set. And in this result, he described all the parameters, right? I have been using this a lot, right? But I didn't pay much attention to the second part. And that's a part give very exciting results for us, right? Was a bit weird in the beginning when I was reading it. I didn't pay much attention. So okay. So here just, so the delta, so big delta equals small delta square. And this one says when P bigger or equal to 5 is a prime, when pi is relative prime to P, then the R has two cases. Either R is even and theta is congruent to 0, modular P minus 1, or R is odd and theta is congruent to P minus 1 over 2, right? And turns out I can use that one to prove a theorem over here. So let G be an abelian group of order P to the 2R U square. P, okay, here, because of the math result, I have to require P bigger or equal to 5 to be a prime number. Now, we require P and U co-prime. And so if D is a Penny type partial difference set in G, then R has to be even. The reason is, so in this case, I can compute my theta. My theta is going to be equal to 0. And so since my theta, I compute it to be 0, so it has to be this case. So that's how I proved R is even. All right, so R is even. So that means 2R will be multiple of 4, right? So that's how we got the corollary. And so this will be, so all of them, we can show that will be AR1, AR2, ARK will be all multiple of 2, will be even numbers. And so that's why the order of the group has to be n to the 4th or 9n to the 4th. Right. And now people will say, okay, how about if the order of G equals to n to the 4th or 9n to the 4th, can you find them? Yes, the answer was ready for me. So John Paul proved in 2010 that n be a part of odd numbers, and he did do constructions of Paley partial difference sets in both groups, I mean, both type of groups of order n to the 4th and 9n to the 4th, right? Now, so I said, okay, if you have it, it must be in those groups. And John Paul Hill said, okay, we do have it, right? He has constructions in his GSATA paper from 2010. So because of that, and so we fully answered question 1, right? So question 1 says, if V is the odd positive integer, and then there exists Penny type PDS in some abelian group of order V, either V is a prime power, V congruent to 1 modulo 4, or V equals to n to the 4th or 9n to the 4th. And why 9n to the 4th? And so math theorem will answer you. So there require P bigger or equal to 5. So okay, so so now I want to talk about the current and future work. So the first thing is maybe we can generalize the Benson type theorem to strongly regular graphs with non-integer eigenvalues and directed strongly regular graphs. Okay. And another one is, can we classify partial different sets in abelian groups of order p to the odd? Now, Suxing was asking me, so most of the time I've been doing existence questions, but in our 4p square case, we did give this sporadic case construction, right? We did recover it. Can we use the method like characteristic matrix to do some constructions, right? So that would be nice to take a look. Another lecture question, which is a difficult question, I will say, to answer question 2 of the Penny type PDS. So in the abelian groups, suppose you know we do have Penny type PDS in order of order V. Can you talk about the structure of the group? Which there are a lot of research going on there, but still remains difficult to talk about the structure of the group to allow Penny type PDS. Another question is, recently Eric Schwartz and his student Toschek, they applied Zeying Wang to provide restrictions on the parameters of PDS in both abelian and non-abelian groups. And this paper, I think, just published recently by JCD. And so can we find more applications of the Benson type theorem? And so, all right. Thanks.
Thank you, Zeying. Thank you for the very nice talk. If you can, please unmute and clap for Zeying. All right, questions or comments?
Thank you for the nice talk. So I have a related question about strongly regular graphs. So my research interest is about Pelly graphs and particularly about the kick number or the classification of the kicks of Pelly graphs. So do you think